4 astronauts are about to hit Earth's atmosphere at 25,000 miles per hour, and for 5 straight minutes, nobody on the ground will be able to talk to them, see them, or help them. That is not a malfunction. That is the plan. Now add a geomagnetic storm on splashdown day, a radiation environment that has been silently cooking the spacecraft electronics for 5 days, and a heat shield that has never been tested this way with humans on board. What you're about to hear is every risk factor converging into one irreversible window, and by the end of this video you will understand why the next 48 hours could define the future of human spaceflight. If this has you hooked, make sure to subscribe to the Skylab so you do not miss the next update as this unfolds in real time, and drop a comment. I want to know where in the world you're watching this, what time it is for you, and your honest opinion. 4 humans, Mach 32, a defective heat shield, and a 48-hour window with no second chance. Safe ride home? Or is this the moment that makes history for reasons nobody wants to see? Let me know in the comments. Now settle in and let's get into it. Part 1. The convergence event no one is framing correctly. Right now, as you're watching this, 4 human beings are falling toward Earth at thousands of miles per hour inside a capsule that has never carried a crew through what comes next. And almost nobody is talking about what is actually about to happen. We have been conditioned to think of spaceflight risk in terms of singular catastrophic moments. The launch explosion, the oxygen tank rupture, the foam strike on ascent. We wait for the one thing that goes wrong, the single dramatic failure we can point to on a timeline and say, there, that is where the mission broke. But the Artemis II return does not work that way. The danger is not one thing. It is everything arriving at the same time inside a 48-hour window that is already closing. Let me reframe what this mission actually is right now. Forget the word journey. Forget the word homecoming. What is happening in this moment is a multi-system synchronization problem collapsing into one fixed atmospheric entry event. The crew is past the moon, they are inside the return corridor, and the physics of that corridor do not offer a second attempt. There is no circling back, there is no parking orbit, there is no pausing to troubleshoot. Every system, every environmental variable, every mechanical sequence must converge into a single window of roughly 5 minutes where this capsule either survives re-entry or it does not, and the clock on that window is already running. Now here is the part that should get your attention. For 5 consecutive days leading up to this re-entry window, the greater than 2 mega-electron-volt electron flux measured by NOAAs goes, satellites has been elevated, peaking at around 7,359 particle flux units. That number probably means nothing to you yet, so let me explain why it should. When most people hear space radiation risk, they think of solar flares. They picture a sudden violent eruption from the sun blasting a wave of energy toward Earth, something dramatic and immediate. But that is not what is happening here. This is not a flare. This is not a coronal mass ejection slamming into the spacecraft. This is something quieter, slower, and in some ways more insidious. The electron environment around Earth and throughout cislunar space has been running hot for days, not spiking, persisting. And that distinction changes everything about how the risk works. Electrons in this energy range, above 2 mega-electron volts, do not behave the way most people imagine radiation behaves. They do not flash burn biological tissue the way high-energy protons do. Instead, they do something engineers lose sleep over. They penetrate spacecraft surfaces, they pass through outer shielding, and they bury themselves in insulating materials inside the vehicle, dielectric materials, cable sheathing, circuit board substrates, the stuff that is supposed to keep electrical pathways separated and clean, and there, inside those materials they accumulate, silently, invisibly. Charge builds over hours, then days, like static electricity collecting on a wool sweater in winter, except the sweater is the insulation protecting your flight avionics, and the discharge is not a harmless spark on a doorknob. It is a voltage spike inside a system that is about to fly through a plasma sheath at Mach 32 with no communication link to the ground. This is the part of the 48-hour convergence that nobody is framing correctly. The spacecraft is not approaching a radiation event. It has been soaking in one for days. And the danger is not that something will suddenly go wrong. The danger is that something has been slowly, invisibly degrading and you will not know it until the moment you need that system to perform flawlessly during re-entry. In low Earth orbit, the International Space Station deals with electron charging events periodically. The station's massive solar arrays and metallic structure act as both collectors and dissipators of charge. And even then, even with active grounding systems and decades of operational experience, engineers have documented anomalous discharge events linked to sustained electron environments. The ISS, though, has the advantage of sitting inside Earth's magnetosphere. It has a magnetic umbrella overhead, deflecting and trapping the worst of what the sun throws at it. The Artemis II crew does not have that umbrella. For most of their return transit, they have been outside the magnetosphere or in its outer fringes, exposed to the full interplanetary particle environment, with nothing between them and those persistent electron streams except the walls of the Orion capsule. And here is what makes duration matter more than peak intensity. A single spike of high electron flux can be absorbed and managed. Charge builds, then bleeds off through grounding paths and natural dissipation. But 5 days of sustained elevation does not give the system time to reset. The charge accumulates faster than it bleeds. Layers of insulation that would normally tolerate brief exposure begin holding more and more trapped charge, and the voltage differential across those layers creeps upward. Engineers call this deep dielectric charging, and the reason it is so concerning is that the discharge, when it finally comes, is unpredictable. It does not happen at a threshold you can set an alarm for. It happens when some combination of temperature change, mechanical vibration, or material fatigue weakens the insulation enough to allow a breakdown. And when does a spacecraft experience sudden temperature change, mechanical vibration, and material stress all at once? During atmospheric re-entry. That is the convergence. That is the thread you need to hold onto for this entire video. The 48-hour window is not dangerous because of any single factor. It is dangerous because the accumulated invisible stress of days of electron exposure is about to meet the most violent mechanical and thermal environment the spacecraft will ever face, and it is all happening inside a window where there is no abort, no second pass, and no communication with the ground during the most critical 5 minutes. The spacecraft is already in the storm. It just does not look like one. There is another layer to this that rarely gets discussed in public because it does not come with dramatic imagery or alarm sirens. When high-energy electrons slam into the metallic structure of a spacecraft, they decelerate rapidly, and that deceleration produces secondary X-ray radiation called Bremsstrahlung. The word is German. It means braking radiation, and it means that the aluminum and steel meant to protect the crew and the avionics from the external particle environment are themselves becoming sources of secondary radiation on the inside. The shielding is generating its own low-level X-ray field. Not enough to pose an acute biological threat to the crew, not by a wide margin, but potentially enough to add a subtle noise floor to sensitive electronics over a multi-day exposure. This is the kind of thing that does not make headlines because there is nothing to photograph. There is no visible storm outside the window. Telemetry screens look calm. The crew reports feeling fine, and the public, watching tracking feeds and mission updates, sees a spacecraft gliding smoothly home. The psychological mismatch between what that looks like and what is actually happening at the particle level inside the vehicle's walls is enormous. It is like watching a house that looks perfectly stable from the outside while termites have been eating the framing for a week. You would never know until something bears weight it can no longer carry. There is an emerging hypothesis among radiation engineers, not confirmed, not published as consensus, but circulating in the technical discussions, that cumulative electron environments of this duration may subtly affect avionics noise margins, not cause failures, not trip circuit breakers, but narrow the margin between normal signal and noise just enough that under high-stress operational conditions, error rates could tick upward. A bit flip here, a sensor misread there. Nothing catastrophic in isolation. But inside a re-entry sequence where every automated response must execute within milliseconds, narrowed margins matter. So let me tie this back to where we started. The Artemis II crew is not approaching the danger zone. They have been inside it for days. The electron storm is not a future event on their timeline. It is the environment they have been marinating in. And every hour they soak, the invisible stress on their vehicle's internal systems ticks upward by an increment too small to trigger any alarm, but too real to ignore when you understand what comes next. Because what comes next is a heat shield that has never done exactly this before, a re-entry angle with no room for error, and 5 minutes of plasma blackout where the entire spacecraft becomes a sealed box, falling through fire with no link to anyone on the ground. That 48-hour convergence window is not opening soon, it is already open. And everything that happens from this point forward feeds into one irreversible moment. But before we get to that moment, we need to talk about the one piece of hardware that stands between the crew and 5,000-degree plasma. And the unsettling truth is, nobody knows exactly how it is going to behave. Not the engineers, not the simulations, not even the material itself. Part 2. The heat shield decision. That quietly defines everything. The heat shield on the Orion capsule is made of a material called Avecoat, and that name carries a lineage that sounds reassuring until you examine what it actually means for this specific mission. Avecoat is an ablative thermal protection material. Its job is straightforward in principle: absorb enormous heat energy by sacrificing itself, charring and eroding layer by layer so that the structure behind it stays cool enough to survive. The Apollo capsules used a related ablative concept, and Avecoat itself was part of that program's thermal protection heritage. So when NASA selected it for Orion, the logic seemed sound. Proven concept, known material family, decades of thermal engineering data to draw from. Then Artemis I flew, uncrewed, November 2022. And the heat shield came back with unexpected damage. The material had shed in ways that were not predicted by pre-flight models. Pieces of the ablative surface had cracked and separated. Char layers showed uneven erosion patterns. The word NASA used publicly was loss of material, which sounds clinical and manageable until you realize what it implies. The thermal protection system behaved in a way the models did not anticipate, on an uncrewed test flight, under conditions the vehicle was specifically designed to handle. The root cause, simplified as clearly as I can make it, comes down to what happens when you fly a skip entry trajectory. On Artemis I, the capsule entered the atmosphere, pulled up and skipped back out briefly, then re-entered for final descent. That skip creates two distinct heating cycles. The material heats up, cools slightly during the skip, then heats again. During that cooling phase, trapped gases inside the ablative material, gases generated by the charring process itself, found themselves under shifting pressure conditions. When the second heating cycle began, those trapped gases expanded, and in some areas they burst outward through the char layer, taking chunks of material with them. Now, that finding alone would be concerning enough. But what matters for this video, for this 48-hour window we're tracking, is what NASA decided to do about it. And what they decided reveals the engineering trade-off that quietly defines this entire re-entry. They did not redesign the heat shield. They did not replace Avecoat with a different material. They did not rebuild the thermal protection system from scratch. What they did was change the trajectory. Artemis II will not fly a skip entry. It will fly a direct entry, a single continuous plunge into the atmosphere, without the skip maneuver that caused the thermal cycling problem on Artemis I. One heating event, one monotonic rise in temperature, no cooling gap, no pressure reversal, no trapped gas expansion cycle. On paper, that sounds like a clean solution. Remove the condition that caused the failure mode, problem solved. But sit with it for a moment, because the engineering logic here is more complicated than it appears, and it connects directly to why this 48-hour window carries the uncertainty it does. They did not fix the material. They changed the thermal history the material will experience. That is a fundamentally different kind of solution. The Avecoat is the same Avecoat, the same chemistry, the same manufacturing process, the same bond to the capsule's substructure. What is different is the heat profile it will see during re-entry. Instead of two heating pulses with a gap, it gets one sustained, continuous thermal load. And that means the question is no longer, will the skip cause gas trapping again? The question is, how does this exact material behave under a continuous high-energy heating profile that it has never actually experienced on a real mission? The reason they did not redesign the shield is not negligence, it is schedule physics. Replacing a thermal protection system on a crewed vehicle is not like swapping a part. Avecoat is applied in blocks, individually fitted to the capsule's curved surface. Each block is hand-packed, bonded, inspected, and verified. Redesigning the material would mean requalifying every manufacturing step, retesting at the component level, at the subassembly level, and at full system level, then repeating the entire integration process. That is years of work. years the Artemis program did not have if it wanted to maintain its launch window and its political viability. So the decision was made: keep the shield, change the trajectory, validate the new profile through simulation and ground testing, and accept the residual uncertainty. And this is where the 48-hour convergence thread pulls tight. The heat shield is the final physical gate between the crew and survival during atmospheric entry. Every other system, every trajectory correction, every thruster test, every navigation update, all of it is upstream of the moment when plasma closes around the capsule and the AV coat must perform. And that performance is being extrapolated from modelling and ArcJet ground tests, not from a prior crewed flight through this exact thermal envelope. Let me be precise about the uncertainty. Apollo flew smaller capsules at lower velocities with a different ablator chemistry. Artemis I flew a V-coat, but on a skip-entry trajectory. Artemis II is flying a V-coat on a direct-entry trajectory at lunar return velocities with a crew on board for the first time. There is no prior flight data point that matches this exact configuration. The simulations say it will work. The ground tests say the material can handle the expected thermal load. But simulations are governed by models, and models are governed by assumptions, and assumptions are governed by what we have observed before. When you fly a configuration for the first time, you are testing those assumptions with lives in the balance. The engineering debate, the one that does not make it into press conferences, is not about whether the heat shield will fail. No credible engineer is predicting failure. The debate is about failure morphology. If something unexpected happens, what shape does it take? Where on the surface does it occur? How does it propagate? Those are questions that simulation can constrain but not answer definitively, because the real thermal environment includes variables no ground facility can perfectly replicate. The exact plasma composition at Mach 32, the turbulence in the shock layer, the interaction between ablation products and ionized air, the structural vibration of the capsule transmitted into the heat shield surface. These are the unknowns that live in the gap between analytical clearance and operational validation. The astronauts aboard Orion right now are trusting a system that has been analytically cleared but never operationally proven in this exact configuration. That is not unusual in spaceflight. Every first flight of a new system carries that gap. But it does mean that the heat shield is not a solved problem, sitting quietly in the background of this re-entry. It is an active variable, feeding directly into the 48-hour convergence window, and its behaviour during the roughly 5 minutes of peak heating will determine whether the mission becomes a triumph or a case study. And if you are starting to sense that this re-entry is stacking unknowns in a way that is uncomfortable, hold that thought, because there is another variable arriving at exactly the same time, one that has nothing to do with the spacecraft itself and everything to do with what is happening between the Sun and the Earth on the day this capsule hits the water. Part 3. The silent wildcard, solar geometry and timing alignment. There is a geomagnetic storm forecast for Splashdown Day. Not a dramatic one. Not the kind that makes headlines about northern lights visible in Florida or power grids under threat. A G1 storm, the lowest classification on the NOAA geomagnetic storm scale. And if you stopped there, at the classification, you would dismiss it entirely. G1, minor. Background noise, barely worth mentioning, but classification tells you magnitude. It does not tell you timing, and timing is everything inside this 48-hour window. The source of this particular storm is a coronal hole high-speed stream interacting with what solar physicists call a correlating interaction region, the boundary zone where fast solar wind from the coronal hole catches up to slower wind ahead of it and compresses into a pressure front. When that front reaches Earth's magnetosphere, it pushes on the magnetic field, distorts it, and drives currents through the ionosphere. The KP index, the standard measure of global geomagnetic disturbance, is forecast to reach around 5. Again, minor by space weather standards, but the effects propagate downward into systems that the Artemis II recovery operation depends on absolutely. Ionospheric disturbance at KP5 introduces propagation delays into GPS signals, not massive delays. We are talking about meters of positional uncertainty, not kilometers. But the recovery of a capsule from the open Pacific Ocean at night is an operation that lives and dies on precision. The Navy recovery team, the helicopters, the swimmer divers who enter the water to secure the capsule, all of them depend on knowing exactly where that capsule is the moment it hits the surface. GPS provides the backbone of that tracking chain, and when the ionosphere is disturbed, GPS accuracy degrades in ways that are probabilistic, not uniform. You cannot predict exactly which signals will be delayed, by how much, or for how long. You can only know that the error bars on your positioning data just got wider at the worst possible moment. High-frequency radio communication, the backup to satellite comms for ship-to-ship and ship-to-aircraft coordination, also degrades under geomagnetic storm conditions. HF radio depends on ionospheric reflection, and when the ionosphere is being pushed and pulled by solar wind pressure, those reflection paths become unreliable. Communications get patchy, signals fade, coordination between recovery assets becomes harder at exactly the moment when coordination matters most. And all of this is happening at night. The splashdown is scheduled during darkness, which means visual tracking of the capsule under its parachutes is limited to radar, infrared, and beacon signals. Each of those tracking methods carries its own error margin, and those margins grow when the electromagnetic environment around them is unstable. The compound effect of GPS drift, HF radio degradation, and nighttime visual limitations does not produce a clean single failure. It produces a smeared, uncertain tracking picture where confidence in the capsule's exact location drifts at the same time the recovery team needs that confidence most. The 48-hour convergence is not just about what happens to the spacecraft. It is about what happens on Earth at the exact moment the spacecraft needs Earth to work perfectly. The reentry is the irreversible commitment. The recovery is the irreversible consequence, and a G1 storm, minor by every standard definition, is introducing wobble into the final chain of events inside the same window where the heat shield faces its first real test, and the accumulated radiation environment reaches its peak influence. Nobody is going to cancel a recovery operation over a G1 storm. Nobody is going to delay splashdown because the KP index hit 5. But understanding this convergence means understanding that the margins in this 48-hour window are being nibbled from every direction simultaneously. And that is what makes the next phase so critical, because now the trajectory itself begins to lock in, and once it does, every one of these overlapping variables becomes irreversible. Part 4. Trajectory correction. Burns as precision traps. There are 3 planned trajectory correction burns that define the final return corridor for Artemis II. Think of them as the last 3 turns of a combination lock. Each one clicks the capsule's path closer to the exact entry angle it needs, and each one removes a degree of freedom that existed before the burn was executed. The first of these burns has already been completed successfully, a small delta-V adjustment, modest in thrust, enormous in consequence. Because what that burn did was begin the process of converting a wide return corridor into a narrow one, and that narrowing is not reversible. Here is why entry angle matters in a way that is absolute, not relative. The Orion capsule must hit the upper atmosphere at a specific angle, measured relative to the local horizon. That angle has an acceptable range, but the range is punishingly small, too shallow, and the capsule skips off the atmosphere like a stone off a pond. It does not re-enter. It sails back out into space on a trajectory that the service module cannot correct because the service module has already been jettisoned. Too steep, and the thermal load exceeds what the heat shield can absorb. The capsule overheats, the structure fails. There is no middle ground outside the corridor. It is a physics tunnel, and the walls are lethal. Each trajectory correction burn makes that tunnel narrower in physical space, but more precise in targeting. The first burn said, "We're going through this region of the atmosphere." The second burn will say, "We're going through this specific slice." The third will say, "We're going through here, at this angle, at this velocity," and no amount of subsequent adjustment will change that. By the time the third burn is complete, the capsule is on a ballistic trajectory aimed at a keyhole in the atmosphere that is, metaphorically, the width of a doorframe at the end of a 240,000-mile hallway. And here is the trade-off that makes this part of the 48-hour convergence so tense. Each burn that increases targeting precision simultaneously decreases recovery options. Before the first burn, the corridor was wide enough that multiple entry solutions existed. If a problem had been detected, the trajectory could have been adjusted to accommodate a different entry point, a different landing zone, a different timing. After the final burn, those options collapse. The capsule is aimed, the physics are set, the entry will happen where the burns say it will happen, when the burns say it will happen, and nothing the crew or ground control does after that point can meaningfully change the outcome. This is what I mean by precision trap. The same process that ensures the capsule hits its target correctly is the same process that eliminates every alternative if the target conditions change. If the geomagnetic storm intensifies beyond forecast, the trajectory is already locked. If the heat shield telemetry shows an anomaly, the trajectory is already locked. If the recovery fleet encounters conditions that degrade their tracking capability, the trajectory is already locked. The burns that are keeping this crew alive by ensuring a survivable entry angle are the same burns that are erasing every escape route. Ground control depends on real-time tracking data to calculate each burn. That tracking data flows through the deep space network, is processed through orbit determination models, and is translated into burn parameters. The entire chain requires precision, and as the capsule gets closer to Earth, the geometry of that tracking changes. Signal latency decreases, which sounds helpful, but the margin for correction also decreases. The burn must be more precise because the remaining flight time is shorter. There is less downstream distance to compensate for small errors. Every parameter tightens simultaneously. There is no abort to lunar orbit option once these burns are finalized. There is no engine on the crew module capable of reversing the trajectory. There is no scenario in which ground control says, "Actually, let us go around and try again." The burns commit the crew to the entry. The entry commits the crew to the heat shield. The heat shield commits the crew to the parachutes. And the parachutes commit the crew to the recovery fleet. It is a chain of irreversible commitments, each one forged by a burn that makes the next link mandatory. The engineering philosophy behind this approach is converge, do not improvise. Deep space trajectory management does not leave room for real-time creativity. You calculate, you verify, you execute, and you trust the math. The crew is trained to understand this. They know that once the final burn completes, they are passengers of physics. Their piloting skills, their training, their judgment, all of it matters for the systems they can control. But the trajectory itself belongs to orbital mechanics now, and orbital mechanics does not negotiate. That narrowing funnel, that precision trap, is the structural backbone of the 48-hour convergence window. Everything else, the radiation environment, the heat shield uncertainty, the geomagnetic storm, the nighttime recovery, all of it exists within a corridor that is physically tightening around the crew with every burn, and the next thing they need to test before that corridor closes completely is whether they can actually fly this spacecraft by hand if they have to. Because if the automation fails during the most critical phase, the question becomes, can a human pilot do what the computer was supposed to? Part 5. Manual piloting tests. Control versus autonomy validation. Somewhere in the transit back to Earth, the Artemis II crew is conducting a test that sounds routine, but carries implications that reach directly into the re-entry sequence. They are flying the Orion capsule manually, hands on the controller, eyes on the displays, thruster firings commanded by a human pilot rather than the onboard guidance computer. The test protocol involves two modes. The first is 6 degrees of freedom control, full authority over translation and rotation in all 3 axes. The crew commands the spacecraft to move in specific directions and rotate along specific angles using the reaction control thrusters. The second is a simplified 3 degrees of freedom mode, where the control inputs are reduced and the spacecraft response is more constrained. Both modes are being evaluated not just for whether they work, but for how they feel. How the vehicle responds to human input. How the lag between command and reaction compares to what the crew trained for in simulators. How the handling characteristics change under real spaceflight conditions versus ground-based modelling. This matters because the vast majority of deep space navigation is autonomous. The guidance computer handles trajectory maintenance, attitude control, and orientation adjustments with a precision that human hands cannot match over long durations. But autonomy is only useful when the autonomous systems are functioning correctly. If the guidance computer encounters an error, if the star trackers lose lock, if the inertial measurement units drift beyond tolerance, someone has to fly this thing, and that someone has to fly it accurately enough to maintain the entry attitude within the corridor that those trajectory correction burns have already defined. The margin between survivable entry and thermal overload is measured in fractions of a degree. A human pilot has to hold that margin with a hand controller, while the capsule is being buffeted by atmospheric interface forces at Mach 32. The manual piloting tests are checking for something specific and subtle: the drift between human intuition and automated control logic. Simulators teach the crew what the spacecraft should feel like. But simulators are models, and models carry assumptions. The real vehicle may respond slightly differently. Thrusters may fire with slightly different impulse profiles. The moment of inertia of the loaded spacecraft may differ fractionally from the simulator's mass model. Fluid slosh in the propellant tanks may introduce dynamics that the simulator approximated but did not replicate exactly. Each of these differences is small in isolation. Together, they create a handling characteristic that the crew is feeling for the first time in actual spaceflight. There is a hidden engineering concern embedded in this test that goes beyond simple system validation. It is about control consistency across crew members. Not every pilot flies the same way. Hand controller input profiles, reaction times, correction strategies all vary between individuals. The control system needs to be robust enough that any trained crew member can maintain attitude control within the required tolerance, not just the specific pilot who happens to be in the seat during the test. Human variability is a design parameter in crewed spacecraft, and validating it means accepting that the system must tolerate a range of input styles without diverging from acceptable response. The connection to the 48-hour convergence window is direct. If the autonomous systems encounter any anomaly during the re-entry sequence, the crew's ability to take over and manually hold the entry attitude is the backup plan. And that backup plan is being validated right now, in the hours before the window closes, with a spacecraft that is simultaneously soaking in a multi-day Electron environment and aimed at a heat shield test that has never been performed with humans aboard. The manual control tests are not a separate line item on the mission timeline. They are a load-bearing element of the convergence architecture. They are confirming or revealing whether the crew can serve as the redundancy layer if automation wavers during the most critical phase of the mission. There is a psychological dimension to this that astronauts talk about in debriefs, but rarely in public. They call them loss of trust moments. The instant when the pilot realizes the automation is not doing what it should, and the decision to take over must happen faster than the analytical mind can fully process. You do not get to pause and evaluate during atmospheric entry. You either trust the computer or you take the stick, and the transition between those two states must happen with zero hesitation and zero overcorrection. That transition is what the manual piloting tests are rehearsing. Not the flying itself, but the moment of cognitive switch between passenger and pilot. And that switch matters more inside this 48-hour window than it would under cleaner conditions, because the radiation environment we discussed in Act 1 does not only affect hardware. It affects the noise floor of the sensors the pilot reads, the displays the pilot interprets, and the thrusters the pilot commands. If cumulative electron charging has subtly shifted the performance of any component in that control chain, the crew's manual flying experience from the test may not perfectly predict what manual flying feels like during the actual entry. The convergence is not just external factors stacking up. It is the interaction between every tested system and an untested moment. Now, I want to come back to that radiation environment, because while we have been talking about trajectory burns and manual control tests, the electron storm has not stopped. It has been running the entire time, and the way it affects the spacecraft is not the dramatic system failure people imagine. It is something slower, quieter, and harder to detect until it is too late to do anything about it. Part 6. Radiation environment as slow system stress. The 2 megaelectron-volt electron flux has not subsided. As the crew prepares for the final phase of return, the particle environment they have been travelling through for days continues to pump energy into the spacecraft's structure at a rate that does not trigger alarms but does not stop accumulating. Let me separate what is happening into 2 categories, because the public conversation tends to collapse them into one, and that collapse hides the specific risk that matters for this 48-hour window. The first category is biological radiation exposure to the crew. This is what most people think about when they hear radiation in space. Energetic particles passing through the body, damaging DNA, increasing cancer risk over time. For this mission, the proton flux, which is the primary driver of biological dose, has remained relatively low. That is a stabilizing factor. The crew is not receiving a dangerous acute biological dose. Their cumulative mission dose is still being evaluated, but nothing in the current data suggests an immediate health threat from particle radiation to the astronauts themselves. That is the good news, and it is important to state clearly. The second category is what matters for the convergence window, and it is not biological at all. It is electrical. Those sustained electron fluxes above 2 megaelectron volts are an electrical engineering problem, not a medical one. And the distinction is critical because the systems at risk are not the humans aboard the capsule. They are the electronics, the sensors, the control circuits, and the communication hardware that the humans depend on to survive re-entry. Let me walk through the mechanism one more time, because it connects directly to what happens when this capsule hits the atmosphere. High-energy electrons penetrate the spacecraft's outer skin and embed themselves in dielectric materials inside. Over hours and days, the trapped charge builds. The voltage across insulating layers rises. This creates a condition where the insulation is under invisible electrical stress, holding more charge than its resting state, waiting for a trigger to discharge. The trigger does not have to be dramatic. A temperature shift, a vibration spike, a material contraction from cooling. Any perturbation that slightly changes the dielectric geometry can initiate a discharge event. And what is atmospheric re-entry if not the most extreme perturbation the spacecraft will ever experience? Temperatures spike by thousands of degrees on the exterior. Vibrations intensify as the capsule decelerates through the atmosphere. Structural loads shift. Materials expand and contract. Every condition that could trigger a charge-discharge event in a stressed dielectric is present simultaneously during the exact phase of flight where system reliability matters most. The analogy I keep coming back to is this. Imagine you've been inflating a balloon very slowly for 5 days. Each breath adds just a tiny bit more pressure. The balloon looks fine. It feels fine. You could hold it and never know it was near its limit, but then someone slaps it. The slap is re-entry. And whether the balloon pops depends on how much pressure 5 days of slow, invisible inflation has actually built up inside it. The secondary radiation, the Bremsstrahlung effect we discussed earlier, adds another layer to this. The spacecraft's own shielding structure has been generating low-level secondary X-rays as a byproduct of stopping those high-energy electrons. Over a single day, the effect is negligible. Over 5 days of sustained exposure, the cumulative secondary radiation field inside the vehicle is measurably elevated compared to a clean radiation environment. This secondary field does not damage components in the way a direct particle strike would, but it contributes to what engineers call the noise floor, the baseline level of electromagnetic interference that sensors and circuits must operate above to function correctly. A slightly elevated noise floor means slightly reduced signal-to-noise ratios on sensor readings, slightly less clean data from star trackers, from accelerometers, from temperature sensors, from the very instruments the guidance computer uses to manage the entry sequence. Again, nobody is predicting failure from this. The systems are designed with margins. The quiet question circulating among the engineers tracking this mission is how much of those margins have been consumed by 5 days of sustained electron bombardment. Because margins are not infinite, they are budgeted, and every source of noise that eats into the budget brings the operating point closer to the line between reliable performance and anomalous behavior. This is the radiation thread within the 48-hour convergence, and it ties directly to everything that follows. The trajectory burns have locked the crew into an irreversible entry. The manual piloting tests have established baseline handling in conditions that may shift under re-entry loads. And the radiation environment has been slowly, silently modifying the performance baseline of the electronics that will manage or fail to manage the most critical 5 minutes of the entire mission. All 3 threads feed into the same moment, and that moment is the atmospheric entry at Mach 32, where physics takes control and the spacecraft stops being an engineering system and becomes a thermodynamic event. That event begins with a wall of plasma and a total loss of communication. Let me tell you exactly what that looks like from inside the capsule. Part 7. Mach 32 as a physics boundary, not a speed. When the Orion capsule reaches entry interface, defined at approximately 400,000 feet altitude, the spacecraft is moving at roughly 25,000 miles per hour relative to the Earth's surface. In atmospheric terms, that is equivalent to approximately Mach 32. But I need you to forget for a moment what you think Mach 32 means, because the number alone does not capture what is actually happening to the vehicle and the air around it. At velocities most people are familiar with, air flows around an object. At supersonic speeds, Air compresses into shock waves ahead of the object, but at Mach 32 the air does not just compress, it transforms. The kinetic energy of the capsule slamming into the upper atmosphere is so enormous that the air molecules in the shock layer directly ahead of the vehicle dissociate. They break apart into individual atoms. Those atoms then ionize. Electrons are stripped from nuclei. The gas ahead of the capsule becomes plasma, a superheated soup of charged particles radiating energy across the visible and infrared spectrum. The capsule is not flying through air anymore. It is flying through a sheath of ionized gas that it is creating by the act of moving through the atmosphere at this speed. And that plasma sheath does something that changes the entire risk calculus of the next 5 minutes. It blocks electromagnetic signals. Radio waves cannot penetrate the ionized shell surrounding the vehicle. Communication between the capsule and the ground ceases. Telemetry stops. Voice contact stops. Tracking data stops. For approximately 5 minutes, the Orion capsule and its 4 crew members are completely isolated from every human being on Earth. No mission controller can see what is happening. No engineer can diagnose a problem. No command can be uplinked. The capsule becomes a sealed, self-contained thermodynamic system, falling through fire with no external input and no external awareness. During this blackout, the capsule's reaction control thrusters maintain its attitude passively, holding the heat shield oriented toward the plasma flow based on the guidance solution that was computed before the blackout began. If that solution was correct, if the entry angle was precise, if the attitude is maintained, the capsule flies through the heating pulse and emerges on the other side with a functioning heat shield and a decelerating trajectory. If something goes wrong during the blackout, there is no mechanism to communicate, no mechanism to receive assistance, and depending on the nature of the failure, potentially no mechanism to recover. This is the point I want to anchor clearly in the 48-hour convergence framework. Entry is not a high-risk phase of the mission. Entry is the irreversible climax of the mission. Everything that has happened over the preceding 48 hours, the electron storm soaking the avionics, the heat shield decision, the trajectory burns locking the corridor, the geomagnetic storm affecting recovery, all of it has been accumulating toward this 5-minute window where human engineering either holds or it does not. And during those 5 minutes, there is no human intervention possible. The physics of the heating process itself are commonly misunderstood. Most people, if asked, would say the capsule heats up because of friction with the atmosphere. That is not accurate. At Mach 32, the dominant heating mechanism is compression, not friction. The air ahead of the capsule cannot move out of the way fast enough. It compresses violently against the heat shield surface, and that compression converts kinetic energy into thermal energy. The shock layer temperature reaches thousands of degrees not because the capsule is rubbing against the air, but because it is crushing the air into a state where thermal radiation becomes the primary energy transfer mechanism. The heat shield is not experiencing friction burn, it is experiencing compression plasma radiation at point-blank range. Inside the capsule, during these 5 minutes, the crew feels the deceleration. The G-forces build as the atmosphere breaks the capsule from 25,000 miles per hour down to subsonic speeds. The forces are within human tolerance, designed to peak at levels the crew is trained for, but they are sustained and they are intense. The vibration environment is severe, the structural loads on the capsule are at their mission maximum, and outside the walls, plasma glows at temperatures that would melt steel in seconds. The Apollo missions experience similar blackout events, but the Artemis scale is different in ways that matter. The Orion capsule has a larger diameter than the Apollo command module, which means a larger frontal area interacting with the atmosphere, which means a different thermal load distribution across the heat shield surface. Larger surface area introduces more complex flow patterns in the shock layer. Edge effects around the heat shield perimeter become more pronounced. The transition zones between the heat shield and the capsule's back shell experience different thermal gradients. None of these differences are beyond engineering analysis, but all of them mean that the Apollo blackout experience is an analog, not a template. The capsule will emerge from blackout at a lower velocity, still supersonic, but below the plasma ionization threshold. Communication will restore, telemetry will resume, and at that instant, ground control will learn for the first time whether the heat shield survived intact, whether the avionics functioned through the plasma environment, and whether the guidance system maintained the correct attitude throughout the heating pulse. Everything that happened during those 5 minutes will only be known after they are over, and what happened during those 5 minutes depends entirely on how the heat shield behaved under conditions it has never experienced before. That is not a rhetorical statement. That is a material science reality that is playing out right now, on this mission, with crew aboard for the first time. Part 8. Heat shield behaviour under unknown thermal sequencing. The plasma environment surrounding the Orion capsule during peak heating reaches approximately 5,000 degrees Fahrenheit. At that temperature, the AV coat ablative material does exactly what it is designed to do. It sacrifices itself. The surface chars, absorbing thermal energy in the process. The charred material erodes, carrying heat away from the capsule structure. The ablation front, the boundary between intact AV coat and charring AV coat, progresses inward through the material thickness, creating a thermal gradient that keeps the inner surface of the heat shield and the aluminum structure behind it within survivable temperature limits. That process is well understood in principle. It has been tested in ArcJet facilities on the ground, where high-energy plasma torches simulate reentry heating conditions on material samples. It was observed in flight on Artemis I, albeit with the unexpected shedding and cracking that prompted the trajectory change for Artemis II. The fundamental ablation mechanism is not a mystery. What is a mystery, or more precisely what is an open question, is how that mechanism performs across the full surface of a 5-meter diameter heat shield under continuous direct entry heating at lunar return velocities, because that specific test has never been run, not on the ground, not in flight. It is being run right now, with this crew, on this mission. The direct entry profile eliminates the skip entry thermal cycling that caused problems on Artemis I. That is genuinely a risk reduction. But it introduces a different thermal history. Instead of 2 heating pulses separated by a brief cooling period, the heat shield experiences one sustained heating event. The temperature rises continuously, peaks, and then decreases as the capsule decelerates. There is no cooling gap. There is no pressure reversal. The thermal gradient through the AV coat thickness is monotonic, always increasing toward the surface, always driving the ablation front inward. That sounds simpler, and in some ways it is. But continuous heating at this scale introduces its own unknowns. The full surface thermal gradient distribution, meaning the way heat is spread across every square inch of that 5-meter shield, depends on the plasma flow pattern in the shock layer, and the plasma flow pattern depends on the capsule's precise attitude, its exact velocity, the atmospheric density at each altitude, and the geometry of the ablation surface itself, which changes as material erodes. It is a coupled problem. The heating changes the surface, and the changed surface changes the heating. Modelling that interaction at full scale, across the entire shield, with all the local variations in material thickness, bond quality, and surface geometry, pushes the limits of computational fluid dynamics. Ground testing helps, but no ground facility perfectly replicates the conditions of actual lunar return. ArcJet tests expose small material samples to representative heat fluxes. They validate the ablation rate, the char performance, the thermal conductivity assumptions, but they test patches, not the full system. They cannot reproduce the full surface flow interaction, the structural vibration transmitted from the capsule into the shield, the pressure distribution across a curved surface at hypersonic velocity, or the way ablation products from one region of the shield interact with the plasma flow over adjacent regions. The risk framing here is not about probability of failure. Engineers do not approach this as the shield has a 2% chance of failing, or any other number. They approach it as an unknown failure morphology problem. If, despite all analysis and testing, the heat shield encounters a condition that exceeds its tolerance, where does the failure start? Does a localized hotspot develop where the plasma flow stagnation point shifts unexpectedly? Does erosion proceed unevenly, creating a surface geometry that further concentrates heating? Does the bond between the AV coat blocks and the substructure weaken at a localized point, creating a separation that exposes the aluminum structure underneath? These are not predicted failure modes. They are the kinds of failure modes that exist in the gap between what has been simulated and what has been experienced in flight. This connects back to the convergence window in the most direct way possible. The heat shield is the last physical barrier between the crew and the plasma environment. If it performs as modelled, the capsule survives re-entry with margins to spare. If it deviates from the model in any significant way, The nature of that deviation determines the outcome, and the crew will have no ability to respond during the plasma blackout. The heat shield's performance is binary in outcome but continuous in uncertainty. It will work, or it will reveal a failure mode that no one predicted, and either result will be known only after the 5 minutes of blackout end. There is one more piece of this puzzle that needs to be put in place before we move forward, and it is the piece that makes the entire heat shield question harder than it needs to be. It is the assumption, embedded in public commentary and even in some technical discussions, that because Apollo did this 50 years ago, the problem is basically solved. That assumption is wrong, and understanding why it is wrong matters for grasping the true position of this crew inside the convergence window. Part 9. Apollo Analog. Breakdown. Why comparisons fail. The instinct to compare Artemis II to Apollo is understandable. Both programs return crews from the Moon. Both use capsule-based reentry. Both rely on ablative heat shields. The Apollo program did this 9 times between 1968 and 1972, and every crew came home alive. That track record feels like a foundation of confidence. It feels like proof that we know how to do this. And in a broad sense, it is. The fundamental engineering concept of ablative thermal protection during high-speed re-entry was proven by Apollo. But the Artemis II Orion capsule is not an Apollo command module. It is not a larger version of one. It is a structurally and thermodynamically different vehicle entering the atmosphere under different conditions, and the differences are not cosmetic. They are load-bearing. The Apollo command module had a diameter of just under 13 feet. The Orion capsule has a diameter of just over 16 feet. That 3-foot increase in diameter does not scale linearly in its effects. A larger frontal area means a larger stagnation region on the heat shield, where the plasma flow compresses most intensely. It means different shock layer geometry. The angles at which the shock detaches from the capsule edge, the way the plasma wraps around the heat shield shoulder, the turbulence patterns in the wake region, all of these change non-linearly with diameter. Thermal analysis validated for a 13-foot capsule does not automatically extend to a 16-foot capsule. The heat shield chemistry is different. Apollo used an ablative material based on an epoxy Novolac resin system. Avco uses a different formulation. Both are ablators, both work on the same principle, but their charring behavior, their thermal conductivity at different temperature ranges, their mechanical response to structural loads, and their interaction with the plasma chemistry of the shock layer are all material-specific properties that do not transfer between formulations. Testing and analysis must establish AV-Coat's performance envelope independently of Apollo's heat shield data. The Apollo experience informs the approach. It does not validate the hardware. The entry velocities also differ. Artemis II returns from a lunar distance trajectory at velocities that are at the upper range of Apollo equivalent entry speeds, and the Orion capsule is significantly heavier than the Apollo command module. More mass at the same velocity means more kinetic energy that must be absorbed during re-entry. The thermal load budget is different. The deceleration profile is different. The time spent in the peak heating regime is different. Scale effects compound these differences in ways that are difficult to fully capture in ground testing. Larger surfaces propagate stress differently than smaller surfaces. Ablation uniformity across a 5-meter shield is a different engineering challenge than across a 3.9-meter shield. Edge effects, where the heat shield meets the back shell, scale differently. Thermal expansion mismatch between the Avcoat and the substructure is a function of shield area, and larger area means more total mismatch displacement. The engineering fallacy at work here is the assumption that heritage equals validation. Just because AV-Coat descends from Apollo-era thermal protection concepts does not mean Artemis II's heat shield is an Apollo-proven system. The material is different, the capsule is different, the entry profile is different, the scale is different. Each of these differences has been individually analysed and addressed in the design, but the integrated system, the full heat shield on the full capsule at full lunar return velocity on a direct entry trajectory, has never flown with a crew. That integration test is happening in real time inside the 48-hour convergence window, and the Apollo experience cannot substitute for it. This is not an argument that the heat shield will fail. The analysis is extensive, the ground testing is rigorous, the engineering teams are among the best in the world, but it is an argument that certainty does not exist in this window. The crew is flying through a regime where the closest historical analogues, the Apollo missions, operated under fundamentally different conditions. Whatever happens during those 5 minutes of plasma blackout will be new data, not confirmation of old data. And once they emerge from that blackout, once the heat shield has either held or not, the mission shifts from a spacecraft problem to an Earth problem, because the capsule is going to hit the Pacific Ocean at night during a geomagnetic storm, and getting the crew out alive depends on a chain of operations that has its own set of vulnerabilities. Part 10. Geomagnetic storm meets recovery architecture. The G1 geomagnetic storm that we discussed earlier is not a background detail. It is not a footnote in the mission timeline. It is not a yellow advisory that gets filed and forgotten. It is an active, measurable, real-time condition that will be present during the recovery window. And to understand why that matters, why a storm that barely registers on the severity scale could become the thread that unravels the final phase of this mission, you need to understand what recovery actually looks like. Because it is not as simple as spotting a capsule in the ocean and picking up the crew. It is nowhere close to that simple. Let me walk you through what the ionosphere is actually doing during a geomagnetic storm, because this is where the problem starts, miles above the recovery fleet, in a layer of atmosphere that most people have never thought about. The ionosphere is a region of the upper atmosphere, roughly 60 to 600 miles up, where solar radiation strips electrons from gas molecules and creates a shell of electrically charged particles surrounding the Earth. Under normal conditions, this shell is relatively stable and predictable. GPS signals from satellites pass through it on the way to receivers on the ground, and those signals pick up a small propagation delay as they interact with the charged particles. Your phone, your car navigation, the GPS receivers on Navy recovery ships, they all correct for this delay using atmospheric models that predict how much the ionosphere will slow the signal. The correction is built in, it works, and under normal conditions the resulting positional accuracy is good enough to put you within a few meters of your actual location. But during a geomagnetic storm, even a minor G1 event, the ionosphere stops behaving predictably. The solar wind pressure distorts Earth's magnetic field, which drives electric currents through the ionosphere, which redistributes the charged particle density in ways that the standard correction models were not built to handle. The ionosphere becomes patchy, irregular. Some regions become denser with charged particles, introducing longer delays. Other regions thin out. The gradients between dense and thin regions shift on timescales of minutes, and the GPS correction models, which assume a relatively smooth, slowly changing ionosphere, start producing corrections that do not match the actual conditions the signals are travelling through. The result is positioning uncertainty. Not dramatic, not catastrophic. We are talking about meters, maybe tens of meters, of additional error in the GPS coordinates. On land, in daylight, with visual reference points, you would never notice. But the Artemis II capsule is going to be floating in the Pacific Ocean, at night, in open water where there are no reference points, no landmarks, no visual cues that allow a helicopter pilot to correct for what the instruments are getting slightly wrong. The GPS coordinates that the recovery fleet is using to navigate toward the capsule's landing point will carry wider error bars than they would on a magnetically quiet day, and those wider error bars translate directly into slower acquisition of the target. Think of it this way. On a quiet day, the tracking data says the capsule is right there, and points to a spot the size of a parking space on the ocean surface. On a G1 storm day, that same tracking data says the capsule is somewhere in this area, and the area is now the size of a football field. Maybe larger, depending on how disturbed the ionosphere is at that moment, and the difference between finding a capsule in a parking space versus finding it in a football field at night in ocean swells is measured in minutes. Minutes that the crew is spending inside a post-reentry capsule that is bobbing in the water, potentially taking on residual heat shield fumes in a vehicle that was designed to survive reentry, not to serve as a comfortable waiting room in the open Pacific. Now layer in the visual tracking challenge. During a daytime recovery, the capsule is visible. Helicopters can see it. Ships can see it. Human eyes can compensate for instrument error because the target is right there, physically observable. At night, that option vanishes. Visual acquisition of the capsule depends on radar returns, infrared signatures from the capsule's residual heat, and the electronic recovery beacon that the capsule transmits after splashdown. Each of those systems provides an independent tracking solution, and the recovery team assembles a composite picture from all of them. GPS provides the backbone of that composite. It is the most precise input, the anchor point around which the other tracking sources are calibrated. When GPS degrades, the composite picture does not just lose one input, it loses its anchor. The radar data still comes in, but it is referenced against GPS coordinates that are slightly uncertain. The infrared track is still valid, but the helicopter carrying the infrared sensor was navigated to its search position using GPS. Every system in the tracking chain is downstream of satellite positioning, and when the positioning wobbles, everything downstream wobbles with it. High-frequency radio communication adds another layer of degradation. The recovery fleet does not operate in silence. Ships talk to helicopters. Helicopters talk to the command vessel. The command vessel talks to mission control. Swimmer divers in the water relay status updates through the helicopter overhead. This coordination network depends in part on high-frequency radio for over-the-horizon communication, and HF radio works by bouncing signals off the ionosphere. The signal goes up, reflects off the charged particle layer, and comes back down to a receiver beyond the horizon. Elegant in principle, fragile in practice. Because when the ionosphere is being distorted by geomagnetic storm currents, those reflection paths become unreliable. The signal goes up, hits a patch of ionosphere that has shifted since the last transmission, and bounces at an unexpected angle. It arrives weakened, garbled, or not at all. The radio operator hears static where there should be a status update. The helicopter crew calls for confirmation and gets silence. The coordination that is supposed to be crisp and sequential becomes halting and uncertain. And this is happening at the moment when coordination matters more than at any other point in the mission. The crew has just survived atmospheric reentry at Mach 32. The heat shield held, the plasma blackout ended, the parachutes opened, the capsule hit the water. Everything that could not be undone has been done, and it worked. The crew is alive, they are floating. And now the last link in the chain, the link that converts survival into rescue, is operating under degraded conditions because a stream of solar wind hit Earth's magnetic field at precisely the wrong time. The re-entry was the irreversible commitment, the recovery is the irreversible consequence, and the consequence is playing out in an electromagnetic environment that is measurably, demonstrably less than optimal. Here is what I need you to internalize about why this matters inside the 48-hour convergence window. A G1 geomagnetic storm by itself on any other day, affecting any other operation, would be a non-event. Recovery fleets have operated under worse conditions. GPS has degraded before, and operators compensated. HF radio has been unreliable before, and crews switched to satellite backup. In isolation, every single effect of this storm has a known workaround. Nobody is going to lose sleep over a G1 storm in a vacuum. But this storm does not exist in a vacuum. It exists inside a convergence window where the heat shield just experienced its first ever crewed direct entry test, where the avionics have been soaking in an elevated electron environment for 5 straight days, where the trajectory was locked into a corridor with no flexibility remaining, where the splashdown is at night, over open ocean, with a sequential recovery chain that depends on every step completing before the next one can begin. The G1 storm is not the danger. The G1 storm is the last layer in a stack of simultaneous conditions, and its contribution is not dramatic. It is not cinematic. There is no explosion, no alarm klaxon, no red warning light on a console. What it does is corrosive. It nibbles at margins. It widens error bars by meters. It delays coordination by seconds. It introduces ambiguity into tracking pictures that need to be precise. And in a mission where every other system is already operating at the edge of its validated envelope, those nibbled margins are not surplus. They are the margins the mission was counting on. Because margins are what this entire 48-hour window is about. Not catastrophic failures, not dramatic malfunctions. Margins. The space between "this will definitely work" and "this should work." The gap between designed for and tested through. The distance between what the models predict and what reality delivers. Every factor in this convergence window is consuming margins. The radiation consumed some, the heat shield uncertainty consumed some, the trajectory lock consumed some, the nighttime recovery consumed some, and now the geomagnetic storm is consuming the last of what is left, in the final phase, at the worst possible time, in the quietest possible way. And nobody, not a single official source is going to call a G1 storm dangerous, because it is not. Until it is the last straw on a stack that has been building for 48 hours. Part 11. Recovery Chain Fragility. Let me walk you through what happens after splashdown, because the public image of capsule recovery tends to compress a complex multi-step, failure-intolerant sequence into a single moment of celebration. You have seen the footage from previous missions. The capsule bobs in the water, helicopters circle overhead, divers splash in, and the next shot is astronauts smiling on the deck of a ship wrapped in towels. It looks smooth, it looks routine, it looks like the hard part is over. The reality is considerably more fragile than it looks on the broadcast, and inside the 48-hour convergence window we have been tracking, that fragility takes on a weight it would not carry on any other day. The capsule hits the water. That sentence is doing a lot of work, so let me unpack what hits the water actually means from an engineering standpoint. The Orion capsule, after descending under 3 main parachutes, impacts the ocean surface at a velocity that is survivable by design but violent by any human standard. The parachutes have slowed the vehicle from hypersonic speeds to roughly 20 miles per hour, which sounds gentle until you remember that this is a multi-ton spacecraft slamming into an incompressible fluid. The impact is cushioned by the combination of parachute deceleration and the capsule's designed water landing attitude, an orientation that allows the base heat shield to absorb the initial contact and distribute the forces across the widest possible surface. The crew is strapped into seats designed to attenuate shock, but it is still a significant impact event. Bones feel it. Spines feel it. Equipment that survived the G-forces of atmospheric reentry now absorbs a second shock in a different direction, as the capsule decelerates from 20 miles per hour to 0 in a fraction of a second. The capsule must then transition from a ballistic object, something that was falling under gravity and parachute drag, to a stable floating object. And that transition is not instantaneous. It is not even guaranteed to happen correctly on the first attempt. The vehicle can end up in what engineers call a stable 2 orientation, which is the polite technical term for upside down. The capsule's center of mass and its buoyancy profile create 2 possible stable floating positions, and one of them puts the heat shield facing up and the crew hatch facing down into the water. If this happens, inflation bags mounted on the capsule must deploy to shift the center of buoyancy and roll the vehicle upright. This system has been tested. It works, but it adds time. Time the crew is spending inverted inside a capsule in the open ocean, at night, in swells, waiting for the physics of inflatable bags to overcome the physics of an unfavorable mass distribution. Assuming the capsule rights itself, either naturally or with the help of the righting bags, it is now floating in the Pacific Ocean. Picture what that looks like from the crew's perspective. The windows are fogged or coated with residue from re-entry. The interior is hot. The air inside carries residual fumes from the heat shield ablation process, gases released by the charring AV coat material that have migrated through the capsule's thermal protection layers and seeped into the cabin over the course of re-entry. Those fumes are not immediately toxic at the concentrations expected, but they are not pleasant, and extended exposure in a confined space is not something anyone wants to prolong. The crew members themselves have just endured sustained G-forces during atmospheric deceleration, forces that compress the spine, force blood toward the lower body, and leave even highly trained individuals physically drained. They have been in microgravity for days before that, which means their cardiovascular systems and vestibular systems are already in a state of readjustment. They're exhausted, physiologically stressed, and sitting inside a sealed capsule that is rocking in ocean swells. The urgency of extraction is not theoretical. It is medical, environmental, and psychological all at once. The recovery fleet has been pre-positioned based on the predicted landing point. Ships and helicopters do not chase the capsule after it lands. They are already waiting in the recovery zone stationed there hours before splashdown, based on trajectory predictions provided by mission control. Helicopters are airborne, carrying swimmer divers who will be the first humans to physically reach the capsule. Those helicopters depend on tracking data to navigate to the capsule's position in the dark ocean. Radar paints a return off the capsule's metallic hull. Infrared sensors detect the thermal signature of a vehicle that just survived 5,000-degree heating and is still radiating residual warmth. The capsule's own recovery beacon transmits a signal that provides a position fix. and GPS, the backbone of the entire tracking architecture, provides the coordinate framework that ties all of these inputs together into a single composite picture of where the capsule is. We already discussed what happens to that composite picture under geomagnetic storm conditions. The GPS error bars widen. The anchor point of the tracking solution becomes fuzzier, and at night, with no visual horizon reference, no visible capsule to fly toward, the helicopter crews are navigating entirely on instruments. Instruments that are working, instruments that are providing data. But instruments whose data carries slightly more uncertainty than it would on a magnetically quiet night. That additional uncertainty translates into search time, not hours of search time, minutes. But minutes matter when the crew is inside a capsule that is designed to float, not to sustain human habitation in the open ocean for extended periods. The swimmer divers deploy from the helicopter into the water near the capsule. These are highly trained Navy personnel who have rehearsed this operation dozens of times. They jump from the helicopter into the Pacific, swim to the capsule, and begin the process of securing it for crew extraction. The first task is attaching a flotation collar, an inflatable ring that wraps around the base of the capsule and stabilizes it against rolling and wave action. This is a manual, physical operation. Hands-on hardware, bodies in the water, conducted in open ocean conditions, in darkness, in swells that push the capsule and the swimmers in different directions. If the sea state is rough, the collar attachment takes longer. If the capsule is rocking, the swimmers have to time their movements to the wave cycle. If their communication with the helicopter overhead is intermittent because HF radio propagation is unreliable due to the geomagnetic storm, they lose the real-time coordination that allows the helicopter to adjust its position, provide lighting, and relay status to the command ship. Every small degradation in the communication chain extends the timeline by increments that feel small individually but compound sequentially. Crew extraction follows stabilization. The hatch is opened and the crew members are assisted out of the capsule one at a time, not all at once, one at a time. Each crew member must be evaluated, physically supported if needed, transferred from the capsule to a life raft, and then either hoisted to the helicopter by winch or transported by raft to the recovery ship. This is a sequential dependency chain in the strictest sense. You cannot extract the second crew member while the first is still being transferred. You cannot begin extraction while the flotation collar is still being secured. You cannot secure the collar while the swimmers are still in transit from the helicopter. And you cannot position the helicopter while the tracking picture is still being resolved against degraded GPS data. Every step depends on the successful completion of the previous step. There is no parallel path, there is no shortcut, there is no way to skip ahead. The hidden risk in this chain is not any individual step failing. Every step has been rehearsed, every step has contingency procedures. The swimmer divers have trained for rough seas, for nighttime operations, for communication blackouts. The helicopter crews have practiced capsule approach under instrument-only conditions. The recovery ship has protocols for every foreseeable scenario. What has not been rehearsed, what cannot be fully rehearsed, is the compound effect of every step in the chain taking slightly longer than nominal, because the communication environment is degraded, the tracking picture is slightly uncertain, and the coordination between assets is slightly slower than it would be on a clean night with a quiet ionosphere. If the command ship cannot communicate clearly with the helicopter, confirmation of each completed step takes longer. If the helicopter cannot relay the swimmer-diver's status reliably, decisions about when to proceed to the next phase of extraction are delayed. If GPS updates on the capsule's drift, because a capsule in the ocean does drift with current and wind, are arriving with wider uncertainty, the recovery team has to reacquire tracking confidence before committing swimmers to the water. Each of these delays is measured in minutes, but the chain has a dozen steps, and if each step absorbs an extra 2 or 3 minutes of coordination latency, the total extraction timeline extends by half an hour or more. Half an hour with 4 crew members inside a sealed capsule in the open Pacific, breathing residual fumes, riding ocean swells in the dark. The 48-hour convergence thread pulls through here with uncomfortable clarity. The crew survived the radiation environment that had been silently stressing their avionics for 5 days. They survived the heat shield test that had never been performed in this exact configuration with humans aboard. They survived the plasma blackout where no one on Earth could see them or help them. They survived the parachute deployment, the last mechanical gate between controlled descent and uncontrolled impact, And now, in the final minutes of the entire mission, the last dependency chain between survival and rescue is operating under conditions that are slightly, measurably degraded by a geomagnetic storm that nobody in any official capacity would classify as dangerous. That is the nature of convergence risk. It does not need a catastrophic failure to produce a bad outcome. It does not need an explosion, a system shutdown, or a structural collapse. It only needs enough margin erosion at enough sequential steps to push the cumulative timeline past a threshold that the mission was not designed to exceed. Each individual delay is within tolerance. Each individual degradation is manageable, but tolerance and manageability are not infinite resources. They are budgets. And every step in this recovery chain is drawing from a budget that has been shrinking for 48 hours. And if the parachute system had not worked, if those 3 canopies had not opened against the night sky and slowed this capsule from hundreds of miles per hour to 20, none of this recovery architecture would matter at all. The ships, the helicopters, the swimmers, the flotation collars, all of it becomes irrelevant without the one mechanical system that makes splashdown survivable in the first place. Which brings us to the last system standing between the crew and the ocean surface, the one that operates entirely outside the world of electronics, software, and ground control. The one where fabric and cord are the final word. Part 12. Parachute system as last mechanical truth. There is a moment during every capsule re-entry where the mission transitions from an electronic system to a mechanical one. It is not a dramatic handoff. There is no alarm that sounds, no indicator light that changes colour, no announcement over the communication loop. It happens quietly, almost invisibly, in the seconds after the plasma blackout ends, after the heat shield has done its work, after the capsule has decelerated from hypersonic to supersonic to subsonic speed, and the atmosphere has thickened enough for fabric and cord to matter more than software and sensors. That moment is parachute deployment, and it is the final act of engineering before physics makes its judgment on whether this crew comes home alive. Everything we have discussed in this convergence window, the electron storm, the heat shield uncertainty, the trajectory locks, the geomagnetic disturbance, the degraded recovery tracking, all of it feeds into a chain of events that passes through this one gate. If the parachutes work, the chain continues. If they do not, the chain ends. There is no conditional path. There is no branching logic. There is only open or not open, and the difference between those two outcomes is absolute. The sequence begins with the drogue chutes, and I want you to understand what their job actually is, because it is not what most people assume. 2 drogue parachutes deploy at high altitude, while the capsule is still moving at several hundred miles per hour. They are not there to slow the capsule down in any meaningful way. The capsule is still far too heavy and moving far too fast for the drogues to provide significant deceleration. Their job is stabilization. During the atmospheric deceleration phase, as the capsule plows through increasingly thick air at rapidly decreasing speed, it accumulates oscillations, it rocks, it swings. It develops rotational dynamics that, left unchecked, would make the vehicle tumble unpredictably. A tumbling capsule cannot safely deploy its main parachutes. If the mains come out while the capsule is swinging wildly, the parachute lines can tangle, the canopies can collide during inflation, the loads can distribute asymmetrically in a way that tears fabric or snaps risers. The drogues exist to prevent that. They are order imposed on chaos. They take a capsule that is pitching and yawing through turbulent subsonic flow and drag it into a stable, predictable orientation where the next step in the sequence can proceed safely. And this is the thing about parachute systems that makes engineers simultaneously confident and nervous. Every step enables the next step and only the next step. The drogues must work for the mains to have a chance. But the drogues working does not guarantee the mains will work. Each phase of the deployment sequence is independent in its failure modes, but dependent in its prerequisites. You cannot skip ahead. You cannot deploy the mains first and attach the drogues later. The sequence is fixed, and it must execute in order completely without interruption. Once the capsule is stabilized and has decelerated to the appropriate speed and altitude, the drogue chutes release. They are cut away from the capsule, and for a brief moment the vehicle is in free descent again, falling without any parachute, decelerating only through atmospheric drag. It is a designed gap, calculated and intentional, but it is a gap nonetheless. A few seconds where the capsule is a falling object with nothing above it. Then the pilot chutes deploy. These are small extraction parachutes, not much larger than the kind of parachute you might picture a skydiver using, and their sole purpose is mechanical extraction. They catch the airstream, inflate, and pull the 3 main parachutes out of their tightly packed compartments and into the rushing air. The pilot chutes are the hands that reach into the container and drag the mains out. Without them, the main parachutes stay packed and the capsule continues to fall. The main parachutes inflate in a controlled sequence, not all at once. A simultaneous full inflation of 3 enormous canopies would produce a shock load that could tear the attachment points from the capsule structure. Instead, the mains inflate in stages, reefed at first, held partially open by lines that restrict their full expansion, and then gradually allowed to open to full diameter in a programmed series of reefing cuts. Each stage increases the drag, increases the deceleration, and increases the structural load on the parachute risers and the capsule attachment points. The loads are distributed proportionally across all 3 canopies, each one bearing roughly 1/3 of the total deceleration force. 3 main parachutes, operating together, bring the Orion capsule down from several hundred miles per hour to a survivable splashdown velocity of roughly 20 miles per hour. The triple main parachute system includes redundancy by design, and this is one of the few points in the entire convergence window where redundancy exists in a meaningful, tested sense. The capsule is designed to survive landing with only 2 of the 3 main parachutes functioning. If one main chute fails to inflate, if a canopy tears, if a riser line snaps, the 2 remaining parachutes absorb the additional load. The descent rate increases, the splashdown velocity is higher, the impact is harder, the crew absorbs more force, the capsule structure takes more stress, but the outcome is survival. The crew is bruised, not killed. The capsule is dented, not destroyed. The system was explicitly designed around the philosophy that a single-point failure in the main parachute array should not be fatal. That design choice cost weight, cost complexity, cost years of testing, and it is one of the most important engineering decisions in the entire Orion program. But that redundancy has a boundary, and the boundary is sharp. The failure mode that does not have a designed recovery is multiple main parachute failure. If 2 of the 3 main chutes fail, the single remaining canopy cannot generate enough drag to decelerate the capsule to a survivable impact velocity. The capsule hits the water too fast, too hard, with forces that exceed the structural limits of the vehicle and the physiological limits of the crew. This is the edge of the parachute system's design envelope. It is the cliff beyond which there is no safety net, no reserve chute, no last-second retro rocket burn, no airbag system, no emergency inflation device. Nothing. The engineering stops here. Either the parachutes hold, or the mission ends in a way that no recovery fleet, no emergency protocol, and no amount of post-event analysis can undo. And this is the part I want you to sit with for a moment, because it connects back to the 48-hour convergence window in a way that is both reassuring and deeply uncomfortable at the same time. What makes the parachute system conceptually different from every other system we have discussed is its relationship to software and electronics. Once the mortifiers and the drogue chutes leave the capsule, once the pilot chutes pull the mains into the airstream, once the canopies begin their reefed inflation sequence, the system is purely mechanical. Fabric, cord, metal fittings, stitching, aerodynamic forces acting on physical surfaces. No computer is flying the parachutes, no guidance algorithm is adjusting their shape, no software update can be uplinked to change their performance during descent. No sensor reading influences their behaviour. They are, in the most literal sense, the last deterministic system in the entire mission chain. They operate on principles that Isaac Newton would have recognised. Drag equals 1/2 times air density times velocity squared times drag coefficient times area. That is it. That is the entire governing equation, and it does not care about anything else that has happened during this mission. That mechanical independence is both the system's greatest strength and its most sobering characteristic. It means the parachutes are immune to the avionics noise floor that has been building from 5 days of electron bombardment. They are unaffected by dielectric charging in the insulation layers. They do not care if a sensor is reading slightly outside its nominal range. They are not vulnerable to Bremsstrahlung secondary radiation. They are not sensitive to the geomagnetic storm that is degrading GPS and HF radio. They exist in a domain that is entirely separate from the electronic and electromagnetic environment that has been pressing against every other system in this convergence window. Fabric does not experience bit flips. Core does not suffer signal-to-noise degradation. The parachutes are the one system in this entire 48-hour sequence that is genuinely, completely independent of every environmental stressor we have been tracking. But that independence cuts both ways, because if the parachutes fail, there is no electronic rescue. There is no software patch. There is no thruster firing that slows the descent. There is no automated backup system that detects the failure and deploys an alternative. The mission has transitioned out of the domain where engineers can intervene, where ground control can uplink a command, where the crew can flip a switch and activate a redundant system. It has entered the domain of physical objects under aerodynamic forces, and in that domain, the outcome is determined by whether nylon and Kevlar and steel fittings do what they were manufactured to do. The crew's lives depend, in this final phase, not on the billions of dollars of avionics and software aboard the Orion capsule, but on the tensile strength of woven fabric and the integrity of stitched seams. There is something both beautiful and terrifying about that reduction. The most advanced crewed spacecraft ever built, returning from the moon with technology that Apollo astronauts could not have imagined, and in the final minutes, it all comes down to whether the parachutes open. The parachute deployment is the final physical safeguard in the 48-hour convergence window. It is the last gate. After the trajectory burns locked the crew into an irreversible entry corridor, after the heat shield absorbed the plasma and protected the capsule from 5,000-degree heating, after the blackout ended and communication returned and the world learned that the vehicle had survived, the parachutes are the remaining variable. They are the boundary between a crewed mission that succeeded at every prior stage and a scenario that no engineer wants to calculate, no administrator wants to brief, and no family wants to imagine. And once they are open, once 3 white canopies bloom against the dark sky, and the capsule's descent rate drops, and the tracking stations confirm stable deceleration, the mission enters its absolute final phase. Not the triumphant final phase you see on television, the uncertain final phase. A capsule bobbing in the Pacific Ocean. 4 crew members inside, exhausted, waiting. A recovery fleet navigating toward them through degraded signal conditions. Swimmer divers preparing to jump into dark water. A dependency chain with no parallel paths and no shortcuts. The parachutes did their job. Now everything that remains depends on whether the margins that have been eroding for 48 hours have left enough room for the last chain in the sequence to complete before the clock runs out. Because the clock is running. It has been running since the electron storm began 5 days ago, and it will not stop until 4 pairs of boots are standing on the deck of a recovery ship. We are not there yet. Part 13. The stacking model. Why this window is unique. Let me pull every thread we have been following back together, because separately each one of these factors can be explained away. Every single one. You can take the electron storm and say the flux levels are elevated but not extreme. You can take the heat shield and say the analysis is thorough and the ground testing is extensive. You can take the trajectory and say the correction burns were executed precisely and the corridor is well within design tolerance. You can take the geomagnetic storm and say G1 is the lowest classification and barely worth mentioning. You can take the nighttime recovery and say the fleet has trained for this and the procedures are proven. And you would be right about every single one of those statements. Individually, not one of these factors exceeds the design limits of the Artemis II mission. Not one of them, taken alone, would cause a mission manager to pause. Not one of them would generate a headline or trigger an emergency review, and that is precisely the point. That is the entire point of everything we have been building toward for the last 2 hours. The danger in this 48-hour window is not that any single system is expected to fail. It is that every margin in every system is being pressed at the same time. And margins are not infinite. They are not abstract concepts written on a whiteboard. They are physical realities built into hardware, baked into thermal models, calculated into trajectory solutions, and allocated across every subsystem of this mission, with the understanding that not all of them will be consumed simultaneously. Let me walk through the stack one more time, not to repeat what we have covered, but to show you what the stack looks like when you stop examining each factor in isolation and start seeing them as a single interconnected system. Because that is what they are right now. They are not separate risks. They are one risk with multiple faces. The electron storm has been running for 5 consecutive days, not at catastrophic levels, not at levels that would scrub a mission or trigger an emergency declaration, but at levels that have been slowly, invisibly, continuously driving charge into the dielectric materials inside the spacecraft's avionics bays. 5 days of accumulation. 5 days of voltage building across insulation layers that were tested for shorter duration exposures at similar flux levels, but not for this exact duration, at this exact energy profile, in this exact mission configuration. The margin between the normal noise floor of the electronics and an elevated noise floor has been partially consumed. How much? Nobody knows precisely. The instruments that would measure internal dielectric charge state do not exist on this vehicle, because you do not fly diagnostic instruments on an operational crewed mission. You fly flight hardware. And flight hardware does not report on its own margin consumption. It either works or it does not, and you find out which one at the moment you need it most. The heat shield has never performed a crewed direct entry at lunar return velocity. I need to say that again because the weight of it tends to slide off when you hear it alongside a dozen other concerns. This heat shield, in this configuration, on this trajectory profile, with humans inside the vehicle, has never been flown. The analysis says it will hold. The ground testing says the material can withstand the expected thermal load. The design margins say there is sufficient safety factor between the predicted heating and the material's tested limits. All of that is true, and none of it is the same as having done it before. The margin between analytically cleared and operationally validated has not been closed, because the only way to close that margin is to fly the mission. Which is happening right now. The validation and the operation are the same event. The test is the mission, and the mission is the test, and 4 human lives are the data points. The trajectory has been tightened by sequential correction burns into a corridor that is precise but inflexible. Each burn refined the entry angle, narrowed the uncertainty, and improved the probability of hitting the thermal sweet spot in the atmosphere. Each burn also consumed a degree of flexibility. The margin between the planned entry angle and a skip-out trajectory is now at its design minimum. The margin between the planned entry angle and a thermal overload trajectory is now at its design minimum. Both margins are adequate. Both margins are what the mission was designed to operate within. But neither margin has room for surprises. If the atmosphere is slightly denser than modelled at the entry altitude, the heating increases. If the capsule's attitude is slightly off from the guidance solution, the effective entry angle shifts. These are variations that the margins are designed to absorb, but they are variations that consume margin, and the margin available is exactly what the burns left behind. No more, no less. Every burn that improved targeting also consumed flexibility, and the flexibility account is now at its planned balance, which is adequate but not generous. The geomagnetic storm is forecast to reach G1 levels during the splashdown window. Not dangerous by any classification standard, not alarming by any operational threshold, but present, measurably present. The ionosphere will be disturbed, GPS signal propagation will carry additional uncertainty, HF radio communication will be less reliable than it would be on a magnetically quiet day. The margin between nominal GPS accuracy and the accuracy the recovery fleet will actually experience has shifted. The margin between reliable ship-to-helicopter coordination and intermittent coordination has shifted. Not dramatically, not in a way that triggers contingency procedures, but measurably, verifiably, in a direction that makes every step of the recovery chain take slightly longer than it would under clean conditions. The recovery is happening at night, over open ocean, with a sequential dependency chain where each step must complete before the next step can begin. The margin between rapid crew extraction and delayed crew extraction depends on tracking precision, communication reliability, sea state conditions, and the physical performance of swimmer divers operating in darkness in the Pacific. Each of those factors is nominal in its individual forecast. The seas are expected to be manageable, the weather is expected to be acceptable, the divers are trained and ready. But none of those factors is as clean as it would be without the geomagnetic storm layered on top. None of them has the full margin it would have if the tracking data were rock solid, if the communications were crystal clear, if the GPS coordinates were precise to the meter, instead of uncertain to the tens of meters. You see the pattern. You have been watching it build for this entire video. No single factor is red, No single margin is busted. Every individual risk assessment, when conducted for its own factor in isolation, comes back with a result that says acceptable. And that result is correct. They are acceptable individually. The electron storm is acceptable. The heat shield is acceptable. The trajectory is acceptable. The geomagnetic storm is acceptable. The night recovery is acceptable. Check, 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 green across the board. The question that nobody can answer with certainty is whether they are acceptable simultaneously. This is what systems engineers call a convergence risk model, and it is one of the most underappreciated concepts in complex system safety. The idea is not complicated. Complex missions do not typically fail because one thing goes catastrophically wrong. The single dramatic failure, the explosion, the rupture, the total system loss, that is the Hollywood version of mission failure, and it does happen, but it is not the most common path to disaster. The more common path is quieter. Multiple things go slightly wrong at the same time. Each deviation is within tolerance. Each anomaly is manageable. Each individual factor examined by itself does not justify stopping the mission or triggering an emergency. But the accumulated margin erosion across all systems, the total consumed margin, when you add up every slight deviation across every subsystem, exceeds the total margin the mission was designed with. Not because any one system failed, because the budget ran out. The safety margin was allocated assuming that most systems would operate at or near their nominal performance, and only one or two would be stressed at any given time. When all of them are stressed simultaneously, the math changes. The budget that was adequate for individual withdrawals is not adequate for a run on the bank. I want to be extremely precise about what I am and am not saying, because precision matters when you're talking about the safety of a crewed space mission. I'm not predicting a failure. I'm not suggesting that the Artemis II crew is in imminent danger. I'm not implying that NASA is acting recklessly, or that the mission should have been delayed. The engineers and flight directors managing this mission are aware of every single factor I have described in this video. They are monitoring the radiation environment in real time. They are tracking the geomagnetic storm forecast. They have analysed the heat shield performance models exhaustively. They have calculated the trajectory to extraordinary precision. They are managing this mission with the rigour, the expertise, and the institutional discipline that crewed spaceflight demands, and they have been doing this for decades. These are the best in the world at what they do. What I am saying is that this 48-hour window is unique. It is unique in the modern spaceflight era because of the specific combination of factors converging inside it at the same time. The sustained radiation environment is not typical. The first ever crewed direct entry heat shield test is not typical. The geomagnetic storm coinciding with the recovery window is not typical. The nighttime ocean recovery under all of these conditions simultaneously is not typical. Each factor alone could happen on any mission. The stack of all of them happening together, inside the same irreversible 48-hour window, is what has no modern precedent. The overlapping of low probability events is a statistical concept that most people dramatically underestimate. Our brains are wired to assess risks one at a time. If someone tells you there is a 1% chance of this going wrong, and a 2% chance of that going wrong, and a 0.5% chance of this other thing going wrong, your intuition says the overall risk is small because each individual number is small. But that is not how compound probability works. When multiple independent factors are all active simultaneously, the combined probability of at least one of them exceeding its expected behavior rises in a way that is not additive. It is multiplicative in its interaction effects. Worse, the interaction between factors creates emergent scenarios that no individual risk assessment captures, because each assessment was conducted for its factor in isolation. The radiation assessment did not model what happens if the heat shield also behaves unexpectedly. The heat shield assessment did not model what happens if the recovery fleet is also operating under degraded communications. Each assessment answered its own question correctly. But nobody asked all the questions at the same time, because asking all the questions at the same time produces an answer that is harder to act on and harder to communicate to the public. This is the reality of the 48-hour convergence window. It is not one risk, it is the intersection of all of them. It is the space where the electron storm meets the heat shield, uncertainty meets the locked trajectory, meets the geomagnetic disturbance, meets the nighttime recovery, and all of them are real, all of them are present, and all of them are converging on the same irreversible atmospheric entry event that will determine the outcome of this mission. The The crew is inside that intersection right now. They have been inside it for days since the electron storm began. And the walls of that intersection are closing with every passing hour, every trajectory burn, every minute closer to the entry interface where physics takes over and human engineering either holds or it does not. And the answer to which one it will be is coming soon. Very soon. Part 14. Historical Echo Problem, Apollo 13 versus Artemis II. When people search for a comparison point to assess how dangerous this moment is, they reach for Apollo 13. It is the instinctive analogue, the one that lives in the public memory as the definitive spaceflight emergency. Crude lunar mission, life-threatening crisis, dramatic return to Earth. Tom Hanks floating in a freezing capsule saying, "Houston, we've had a problem." The emotional arc of Apollo 13, the ingenuity under pressure, the improvised carbon dioxide scrubbers, the calculated engine burns using the lunar module as a lifeboat, the nail-biting re-entry where nobody knew if the heat shield had survived the explosion, provides a narrative framework that feels directly applicable to what we are watching unfold with Artemis II. It feels like the right comparison, it feels like the right lens, and that instinct is understandable because Apollo 13 is the only reference point most people have for a crewed lunar mission in serious jeopardy. But the comparison breaks down under technical scrutiny. And understanding exactly where it breaks down, understanding why the Apollo 13 framework does not map onto the Artemis II convergence window, illuminates something genuinely new about what this crew is facing. Something that does not fit neatly into any historical narrative we have. Something that is, in its own quiet way, more unsettling than an oxygen tank explosion. Apollo 13 was an internal failure. Let me be specific about what that means. On April 13th, 1970, an oxygen tank in the service module of the Apollo 13 spacecraft exploded. The cause was later traced to a specific sequence of manufacturing defects and testing oversights that left damaged wiring inside the tank. When the tank was stirred during a routine procedure, the damaged wiring sparked, the oxygen ignited, and the resulting pressure blew the panel off the service module. The crisis was immediate. It was visible. The crew heard the bang. They saw warning lights. They watched pressure readings drop. They could look out the window and see debris and venting gas. The ground team saw telemetry spike, saw systems going offline, and within minutes had a working diagnosis of what had gone wrong. The problem was enormous, but it was legible. Engineers could see it. They could measure it. They could isolate the damaged systems from the functioning ones. They could inventory the remaining resources, power, water, oxygen, propulsion, and calculate exactly how much of each they had and how long it would last. They could engineer solutions in real time, improvising workarounds using the materials aboard the spacecraft, because the nature of the failure was specific enough to define what needed to be worked around. The carbon dioxide scrubber hack, the powered-down coast back to Earth, the desperate re-entry without knowing if the heat shield was intact, all of these were responses to a known, identified, diagnosable problem. The risk was enormous, but the path through it was visible, even if it was narrow. The Artemis II convergence is not an internal failure. I need you to absorb that distinction fully because it changes everything about how you evaluate the risk. Nothing inside the Orion spacecraft has malfunctioned. No tank has exploded. No system has gone offline. No warning light has illuminated. No pressure reading has dropped. No telemetry has spiked. The vehicle is performing nominally. The crew is healthy. The trajectory is on target. The heat shield is intact. The avionics are functioning. The communication links are active. If you looked at the mission status board right now, every indicator would be green. Every system would be within its operating range. By every internal metric, this mission is going exactly as planned. What is happening is not inside the spacecraft, it is outside it. The environment around and ahead of the spacecraft is stacking conditions that collectively press against the margins of multiple systems simultaneously. The electron storm did not break anything. It has been slowly, invisibly stressing the electromagnetic environment inside the vehicle. The heat shield has not failed. It has never been tested in this exact configuration with a crew aboard. The trajectory has not deviated. It has been locked into a corridor that is precise but unforgiving. The geomagnetic storm is not disabling anything. It is gently degrading the tracking and communication systems that the recovery fleet depends on. No single thing is broken. The environment is simply pressing on everything at once. And this is why the Apollo 13 comparison fails as a technical framework. Apollo 13 was a crisis. It had a cause, a diagnosis, and a response. The Artemis II convergence is not a crisis. It is a condition. And conditions are fundamentally harder to dramatize, harder to diagnose, and harder to solve than crises. A crisis gives you something to fix. A condition gives you something to endure. A crisis focuses attention on a single point of failure. A condition disperses risk across every system simultaneously, and there is no single action you can take to resolve it. You cannot vent a tank and stabilize the situation. You cannot power down non-essential systems and conserve resources. You cannot improvise a workaround from duct tape and cardboard. The condition is the environment, and you cannot fix the environment. You can only fly through it and hope that the margins hold. Solar cycle variability is a factor that Apollo never had to contend with, in the way Artemis II does. We are currently in solar cycle 25, which by every major metric has been significantly more active than the predictions that were in place when Artemis II was being designed and its mission timeline was being planned. The sustained electron environment, the elevated flux levels we have been tracking for 5 consecutive days, the geomagnetic storm forecast for splashdown day, the general solar wind conditions during this transit, all of these are products of a solar cycle that is running hotter than the model said it would. The planning baseline for the Artemis II return assumed a certain range of space weather conditions. The actual conditions are within the broader design envelope of the spacecraft, but more dynamic and more persistent than the nominal planning case anticipated. That does not mean the mission should not have launched. Solar cycle predictions are probabilistic, not deterministic. You cannot wait for a perfectly quiet sun before flying a lunar mission, because the sun does not offer perfectly quiet windows on demand. Mission planners accept a range of solar conditions and design the vehicle to handle that range. But there is a difference between accepting a range and experiencing the active end of that range for an extended period during the most critical phase of the mission. The crew is flying through the real solar environment, not the modelled one, and the real environment has been more energetic, more persistent and more dynamic than the model predicted for this specific transit window. Modern crewed missions depend more heavily on environmental predictability than Apollo missions did, and this is a point that gets lost in the nostalgia for the Apollo era. Apollo had simpler avionics, fewer sensors, more tolerance for analog noise in its electronic systems. The guidance computers were rudimentary by modern standards, running on kilobytes of memory with cycle times that a modern wristwatch would outperform. But that simplicity came with a form of resilience. Systems that are crude are also systems that are hard to perturb. An analog circuit with wide tolerance bands does not care much about a slightly elevated noise floor. A digital sensor with a precise calibration threshold cares enormously. Orion systems are generations more capable than anything Apollo carried. The guidance algorithms are more sophisticated. The sensor suite is more comprehensive. The flight software can manage scenarios and execute maneuvers that Apollo's computer could not have attempted. But capability comes with sensitivity. More precise sensors have tighter noise tolerances, which means they are more affected by a sustained radiation environment that elevates the electromagnetic noise floor. More sophisticated algorithms depend on cleaner input data, which means they are more vulnerable to subtle signal degradation from charged particle effects on sensor electronics. The spacecraft can do more, but it requires more from its environment to do it correctly. It demands a cleaner electromagnetic background, a more predictable signal environment, a more stable baseline. And this 48-hour window is not providing that. It is providing an environment that is noisier, more disturbed, and more variable than the nominal operating case. The risk paradigm has fundamentally shifted between Apollo and Artemis. Apollo's primary risks were hardware failure and human error. A valve sticks, a switch is thrown in the wrong sequence, a weld fails under pressure, a wire shorts. These are internal risks. They originate inside the system. They are controllable through design, through testing, through quality assurance, through training, through procedures. You can reduce them, you can mitigate them, you can build redundancy against them, and when they occur, you can diagnose them and respond. The entire Apollo emergency response architecture was built around the assumption that risks come from inside the spacecraft, and the solution comes from the ingenuity of the people operating it. The Artemis II convergence window represents a different category of risk entirely. It is an environmental synchronization risk. It does not originate inside the spacecraft. It originates in the timing overlap of external factors that are individually manageable, but collectively unprecedented in this specific combination. The electron storm is a solar phenomenon. The geomagnetic storm is a magnetospheric phenomenon. The heat shield uncertainty is a consequence of program schedule decisions made years ago. The trajectory lock is a consequence of orbital mechanics. The nighttime recovery is a consequence of mission timing. None of these factors is a malfunction. None of them is an error. None of them is a failure of design or execution. They are simply conditions that happen to be present at the same time, inside the same irreversible window, pressing on the same margins from different directions simultaneously. Apollo 13 showed us what happens when a spacecraft breaks. It showed us the heroism of engineers and astronauts improvising solutions under impossible pressure to bring a crew home from a specific, identifiable hardware failure. That story is inspiring and it is earned, but it is not the story that is unfolding right now. The Artemis II convergence window is showing us something different. It is showing us what happens when nothing breaks, but everything presses at once, when every system is green, but every margin is thinner than it should be, when the spacecraft is nominal, but the environment is not, when the engineering is sound, but the universe is not cooperating on the timing. That is a harder story to tell because there is no villain, no explosion, no single moment of dramatic failure. There is only the slow, distributed, invisible accumulation of stress across every system simultaneously, converging on an irreversible event that is now hours away. That distinction matters for understanding why Apollo comparisons, while emotionally powerful, are technically incomplete as a framework for evaluating what this crew is flying through. They are not fighting a single dramatic failure with ingenuity and duct tape. They are not improvising solutions to a visible crisis. They are flying through a convergence of environmental conditions that has no direct historical parallel in crewed spaceflight, inside a window that closes permanently when the capsule hits the atmosphere. And the resolution of that convergence, the answer to whether all those pressed margins hold or whether one of them gives, begins in the next few hours when the entry interface arrives and physics takes the controls from human hands. That moment, the moment of atmospheric entry, is the one we have been building towards since the beginning of this video, and it is the one where every thread we have followed, every margin we have tracked, every quiet concern we have named either holds together or it does not. There is no partial outcome. There is no mostly worked. There is only through or not through. Part 15. Final entry. No abort, no loop, no second pass. The entry interface is approaching. Once the Orion capsule crosses approximately 400,000 feet altitude and begins measurable interaction with the atmosphere, every preceding factor collapses into outcome. The electron environment that has been silently stressing the avionics for days meets the thermal and vibrational shock of atmospheric deceleration. The heat shield that was analytically cleared but never operationally tested in this exact configuration meets the 5,000 degree plasma it was designed to withstand. The trajectory that was precision-locked by sequential correction burns meets the atmosphere at an angle that either sustains a survivable deceleration or does not. And the geomagnetic storm that has been degrading the recovery fleet's tracking precision meets the moment when the capsule needs to be found in a dark ocean. There is no abort option at this point. The word abort implies an alternative, a second path, a way to stop what is happening and redirect to a safer outcome. At entry interface, no such path exists. The service module that provided propulsion for trajectory corrections has been jettisoned. The crew module has no engine capable of reversing its velocity or changing its trajectory in any meaningful way. The capsule is a ballistic object with attitude control thrusters. It can orient itself. It cannot redirect itself. It is aimed, committed, and falling. The plasma blackout will sever communication. For approximately 5 minutes, the capsule will be wrapped in ionized gas that blocks every radio frequency. No voice, no data, no telemetry. Ground control will watch the tracking data go blank and wait. The crew inside will feel the deceleration, hear the structural noise, see the glow of plasma through the heat shield, and rely on the systems around them to do what they were designed to do. There is no communication loop, no feedback cycle, no ability for an engineer on the ground to say, "We see something wrong, try this." The capsule is a sealed system executing a pre-programmed sequence in an environment that does not allow mid-course correction. When the plasma clears and communication resumes, the mission enters the parachute dependency chain. Drogue chutes must deploy. Pilot chutes must extract the mains. 3 main parachutes must inflate and decelerate the capsule to survivable splashdown velocity. This is a single chain event. Each step enables the next. No step can be repeated. If the drogues fail, the mains cannot deploy safely. If the mains fail, there is no tertiary system. The spacecraft has transitioned from engineering to physics, and physics does not negotiate. Splashdown itself is a binary outcome viewed at the highest level. The capsule either reaches the ocean's surface at a velocity the structure can survive, or it does not. There is granularity within that binary, variations in impact load, capsule orientation, sea state, crew condition, but the fundamental outcome branches into success or cascade failure, with no middle path that allows recovery. And then, if the parachute's held, if the heat shield held, if the avionics held, if the capsule is floating, the recovery operation begins, in the dark, under a disturbed ionosphere, with GPS error bars slightly wider than normal, with HF radio slightly less reliable than optimal. With a dependency chain that requires each step to succeed before the next one begins, the mission stops being a spacecraft problem at entry interface. It becomes a physics problem that already started. The engineering is locked in, the decisions are made, the burns are executed, the heat shield is what it is, the parachutes are packed the way they are packed, the electron environment has done what it has done, and the 48-hour convergence window, the window we have been tracking from the moment this video started, collapses into a sequence of irreversible events that will determine the outcome of the most ambitious crewed space mission in half a century. 4 human beings are inside that capsule. They trained for this. The engineers prepared for this. The systems were designed for this. But designed for and tested through are different phrases with different meanings. And on this mission, at this moment, the gap between them is being closed in real time with no simulation, no rehearsal, and no second chance. The most dangerous 48 hours of the Artemis II mission did not start when you thought it did. It started when the electron storm began, days ago, quietly, invisibly, while the cameras were pointed elsewhere. And it will not end until 4 crew members are standing on the deck of a recovery ship, breathing open air, with the Pacific Ocean lapping against a scorched capsule behind them. Until that moment, the convergence window is open, and everything, every system, every variable, every margin is inside it.